Hello everyone, welcome to the lecture for Wednesday, April 1st for our online Calculus 2 class. By the time you watch this lecture, if you are watching it on April 1st, this homework on surfaces of revolution will have already been due, right? Because that's due on March the 31st. But remember, you can always ask for an automatic extension, right? So if you are within a couple of days of this due date, you can still request an automatic extension, right? And continue working on that homework. Again, as you know, right, the instructions for requesting an automatic extension here are in your WebAssign announcements over on the right-hand side. Now, an announcement that I have not posted yet, but will be posted by the time you watch this video, is that our sample test for test number 2 is going to be, it will have already been posted by the time you watch this video, so there will be an announcement about that sample test, right? Okay, so that's going to be posted in the usual spot on Blackboard, so we'll follow the same routine as we did for test number 1, right? I'm gonna you can work on that sample test, right, and then eventually I will post the solutions for the questions on the sample test. That test is going to go through partial fractions, which is this homework, right, that we started discussing last time, and I'm going to continue with a couple more examples of partial fractions today. And that is due on Wednesday, April the 8th. So the test will cover through a partial fraction, so it'll cover volume, right, differential equations, volumes, surfaces of revolution, integration by parts. This is a very important part of the test. Integration by parts, and then also integration by partial fractions. So the way that test is going to work, I probably mentioned this before, is I will post the test on Blackboard, right, and you will write down your solutions on either a printout of the test if you want to, or it can be on a separate piece of paper. You'll write down your answers, and then you're going to scan those your answers, right, and then you're going to email them back to me for grading, and those will be due by April the 10th. So I'm going to post the test on Wednesday, April the 8th, and then you'll have to email me your test paper back by April the 10th so that I can grade it. That's the way the test will work. And I'll have instructions. I think they're already posted in Blackboard, but I'll have instructions there for how to scan and email your test solutions back to me. Although that's already a pretty easy process. Okay. All right. So we still have a little bit of time to discuss the test procedures, right? But that is what is coming up. Don't forget, right? I have my virtual office hours. So here's the announcement for the virtual office hours, right? That are going to be held in Zoom. So please take advantage of these, right? If you need to ask me questions. You can log into one of these Zoom sessions, right? Here are the instructions again at one of these times. I have a time every day of the week, and then also, of course, Taylor is continuing her SI sessions via Zoom. I know a lot of you have been attending those. So those are during what used to be our class time, right, when we were still meeting face-to-face. Her Zoom sessions are Monday and Wednesday from 1 to 2 p.m. I am still going to be awarding Flux dollars, right? Okay, so if you're attending the Zoom sessions, I will know that, and so I can award you Flux dollars for attending the Zoom sessions, okay? And then also, of course, you can contact me by emailing me or phoning me, right? This is my office phone, but as I mentioned before, I can still answer that phone number, right? So you can still call me at that phone number. Okay, so that's just kind of a little bit of where we are in terms of the homework and tests and so forth, right? So I'm going to go ahead now and continue with our partial fractions examples, and then after that, we're going to look at our last major integration technique, which is called trig substitution. So it's a form of integration by substitution, but it involves using trig functions. All right. But let's continue here first with our last couple of examples from partial fractions. Let me see if I can find the right notes here. Oh, yeah, here we go. All right, so this is where we stopped in the notes last time. And so let's continue by integrating or finding the antiderivative of this rational expression, right? Integration by partial fractions is helpful when you're trying to integrate a rational expression, right? Remember, that means a fraction formed by two polynomials. And here we have a polynomial in the top. It's a second degree polynomial, right? And then we have also here a polynomial in the bottom. This is a third degree polynomial. And so this is maybe a good opportunity for us to use partial fractions to help us with integrating here this big rational expression. This is a pretty complex one, right? Because we have a high degree in the numerator and also a high degree in the denominator as well. Now remember, we have other techniques for integrating rational expressions, not just partial fractions. So so don't get obsessed here with partial fractions. Sometimes there are easier methods for integrating rational expressions other than partial fractions, so you don't want to overlook those when you're presented with an integration problem that involves a rational expression like this one. One of those techniques, of course, that we can also use to help us integrate rational expressions is long division, remember, but we cannot use long division on this fraction because the degree of the bottom is 3 and the degree of the top is 2. To use long division, you would have to have the degree of the top at least as big as the degree of the denominator, right? Okay, so so indeed it looks like partial fractions might be useful here, but you're only going to be able to use partial fractions, remember, if you can get the denominator to factor. So if the denominator is not going to factor, then you're not going to be able to use partial fractions. So it'll be back to the drawing board, and you'll have to look for some other technique, okay, to try. Now, this looks like a kind of a challenging denominator to factor here, the x cubed plus 2x squared plus x, but actually this is going to factor with not much difficulty, because notice that we can factor first from each one of these terms an x. So you have to notice that first, that you can factor an x out of every term. And when you factor an x out, you get left with x times x squared plus 2x plus 1, right? And now that factors again. X squared plus 2x plus 1 actually is x plus 1 times itself. X plus 1 times x plus 1, right? X squared plus 2x plus 1 is x plus 1 times itself. And now you can write that in maybe a little bit more efficient form as x times x plus 1 squared, right? So our denominator does factor, and that gives us a lot of hope now that we're going to be able to find this antiderivative by using partial fractions. Okay, so let me rewrite the problem now with our factored denominator, which is x times x plus 1 squared. Okay, so you remember now what our scheme is now, right, with in integrating with partial fractions. We're going to try to rewrite this big fraction, right, as the sum of some smaller fractions, okay? And, right, okay, so so I'm going to insert now here some fractions, so that when I add them together, the sum of those three fractions would be the original integrand that we started with. Now, you may be wondering, why did I write down, why did I leave space here for 3 fractions? Because in the prior example, I only left space for 2 fractions. And that's because the way this denominator factored, notice it has here, one of your factors is a square. Okay, so what that means is that when you try to write this big fraction as the sum of smaller fractions, you're going to have to use 3 fractions. One of them will have denominator x, right? Okay, because one of these factors that we got when we factored our denominator was x. Let's say that its numerator is capital A, because we don't know what the numerator will be yet, right, for that partial fraction. But because the x plus 1 is squared, that means I'm going to have to write two separate fractions that correspond to the x plus 1 squared. One of them is just x plus 1 to the first power, and then the second one is x plus 1 squared. All right. Now look, so don't get confused by that. Okay. When you're trying to break a fraction into partial fractions, and you factor your denominator, right, in order to figure out what the partial fractions are. Okay. If one of those factors is squared, you're going to have to write down two fractions that correspond to that squared factor. One of them will be, the denominator will be the factor to the first power, so we would just have x plus 1 to the first power. And then the second fraction corresponding to this factor, x plus 1 squared, will be x plus 1 to the second power. Okay, so you have to recall to do that now when you're, again, trying to break a fraction into partial fractions. If the denominator has a factor that's squared, okay, you're going to have to write one fraction with that x plus 1 to the first power, and then a second fraction with x plus 1 squared. If you don't do that, you're not going to get the partial fractions written down correctly. Let me show you here also, if this were x plus 1 cubed, okay, if this were x plus 1 cubed, fortunately it's not, but if it were, then we would have to write another fraction here. We would have to write a fraction with denominator x plus 1, a fraction with denominator x plus 1 squared, and a fraction with denominator x plus 1 cubed. You have to have all of the individual powers of that factor up to the power that is actually in your denominator. So since this is x plus 1 squared, I only have to write a fraction with x plus 1 to the first power and x plus 1 squared. Okay, so please try to remember that rule. It's going to be easy to forget, but if you don't remember that rule, you're not going to get your partial fractions to work out properly. Okay, so the numerator of the second fraction I don't know, and the numerator of this third fraction also I don't know. So I'm going to call this numerator B, and I'm going to call this numerator C. All right. If I had another fraction, I could call its numerator D, and if I had another fraction, I could call its numerator E, and so on and so forth. All right. So what we're hoping is, right, when we add a over x plus b over x plus 1 plus c over x plus 1 squared, they will all add up to this original fraction, right, that I was trying to integrate. So we have to figure out what are the a, b, and c, right, so that these three fractions will add up to 5x squared plus 20x plus 6 over x times x plus 1 squared. All right, so let's think about adding these three fractions together, right? So if you're, so I'm going to do that off to the side. So if I were adding these three fractions together, a over x, right, plus b over x plus 1 plus c over x plus 1 squared, then your indeed, if you were to add those together, your common denominator will be x times x plus 1 squared. That's going to be the common denominator, not x times x plus 1 times x plus 1 squared, just x times x plus 1 squared. All right, so add these three fractions together. Here's the right denominator. Okay, this is the common denominator. So I need to rewrite all of these fractions, right, so that they have x times x plus 1 squared as the denominator. Okay, let me move down the if I can get my screen to respond to me here. Let me move down the let me move down this. Let me move down this fraction to give myself a little bit of room. Okay, right. So again, when I add these three fractions together, I'm going to end up with a fraction with this, a single fraction with this common denominator. Of course, that's the common denominator that I want, right? Because that's the denominator of my original integrand here, right? All right, so, then how do we change these three fractions, right? How do we build up these three fractions so that they have x times x plus 1 squared as the denominator? Well, notice that first fraction is missing the x plus 1 squared, right? It's got the x in the denominator, but it's missing the x plus 1 squared. That means I have to multiply top and bottom by x plus 1 squared. So I'll multiply the a times the x plus 1 squared, and I'll multiply the x in the bottom by x plus 1 squared. Okay, so that fraction now will have the correct denominator. What about the second fraction? Well, what am I missing from this denominator? I'm missing one factor of x plus 1. I have x plus 1 to the first power, but I don't have x plus 1 squared. So I'm missing one factor of x plus 1, and I'm also missing the x. So that means I have to multiply top and bottom by x times x plus 1. So you have to multiply the b times x plus 1, right? And you have to multiply that x plus 1 times x plus 1, which will give you x times x plus 1 squared, right? When you multiply x plus 1 times x plus 1, you get x plus 1 squared, and I also have to multiply in the x. And finally, what about this third fraction? Well, let's see. I've got the x plus 1 squared, right? But I'm missing this factor of x, so I have to multiply top and bottom by x. So that's what these three fractions will look like when you give them the correct common denominator. And now, when all those fractions have the same denominator, right, you can just add them all together, right? So you would get a times x plus 1 squared, right, plus b times just x plus 1 to the first power, and then plus c times x, right, all over x times x plus 1 squared. But remember, this fraction, right, this fraction has to come out to be the same as the original fraction, right? So, well, what's it going to take for those two fractions to be the same? Well, their denominators are the same, so that's no problem. But the tops, the numerators, right, also have to be the same. So that means a times x plus 1 squared, right, plus b times x plus 1, right, plus c times x. That has to come out to be equal to, I'm not going to have enough room to fit that in there, but that has to come out to be equal to 5x squared plus 20x plus 6. So it's this equation now where, where we're putting the two numerators equal to each other, right? It's this equation that we're going to use to figure out what the a and the b and the c are, okay? All right, now remember, I taught y'all a trick, right? In those last examples from last lecture of how you can deduce what A, B, and C are, right? And there are other ways, by the way, also of deducing what A, B, and C are. But if this trick that we tried last time works, it's a great method. Remember, what you're going to do is try to substitute a strategic value for x, right? So that you can eliminate some of these terms on the left-hand side of this equation. And one strategic choice for x would be x equal minus 1, right? Because if you plug in minus 1 for x, right, these two terms are going to disappear. Ooh, that's nice, because I think that I can figure out what c must be. So when you plug minus 1 in for x, on both sides of the equation, don't forget to do it on both sides of the equation. Well, when you plug minus 1 in for x, right, this becomes 0. So this first term will disappear. So you get 0 plus, and same thing for the second term, right? When you plug minus 1 in for x, this term disappears, so you get 0 again. And then finally, when you plug minus 1 in for x here, you get c times a minus 1. What about what happens on the right-hand side of this equation? Well, you get 5 times minus 1 squared plus 20 times a minus 1, right? And then plus 6. So it looks to me like minus c is going to be equal to, what are these numbers on the right-hand side add up to? Well, 5 times minus 1 squared is 5. 20 times minus 1 is minus 20, right? Plus 6. So what does that look like? Minus c is equal to, is it minus 9? Am I doing that right? 5 plus 6 is 11, minus 20 is minus 9. So minus c is equal to minus 9, which I think means positive c is equal to positive 9. Yay! There we figured out what c is, right? So, so we're 1/3 of the way finding this partial decomposition. We know now what c is. Now we have to just also figure out what the a and the b are, right? Now, I have another strategic choice for x, though, that I could have used, right? Because if I let x be 0, whoops. If I let x be 0, oh, that's not going to get me anywhere, is it there, right? Okay. Oh, no, I made a mistake. Okay, so I wrote this, I wrote this term here down on right. This is a times x plus 1 squared. So the x is not supposed to be there, right? So it's a times x plus 1 squared plus b times x plus 1 plus c times x, right? And so this x shouldn't be here. So that doesn't make any difference in finding the value for c. But it does help me now in using 0 again as a strategic choice for x, because now when I substitute 0 for x, right, these two terms will disappear, because you'll have this term will have a factor of 0, this term will have a factor of 0, but this term does not disappear. That will give you a times 0 plus 1 squared, right, plus 0, this is 0, plus 0, this will become 0, is equal to, and now when you plug in 0 for x on the right hand side, these two terms disappear and you just get 6. Oh, that's nice. This is a times 1 squared, though, which is just a, so yay, now I know what a is also. I know that a is equal to 6, right? Now, really, in a way, you're done, right? Okay, because now you know what a and b are. I think that makes it really easy here to figure out what b is. Let me show you why. Okay, there's not really another strategic choice here you can make for x that will eliminate any of these terms on the left-hand side of this equation. But now that I know what a and c are, I can fill those in. So I have 6 times x plus 1 squared plus b times x times x plus 1 plus c. But I know what c is, right? C is 9. So plus 9 times x, all of that is equal to still 5x squared plus 20x plus 6. Now you can choose any value you want for x, okay, and substitute any value that you like for x other than 0 or minus 1. You can choose any value for x that you like and plug it into this equation, and now you can figure out what b is. So let's try, an easy one would be x equals 1, right? So if I plug 1 in for x, I would have 6 times 2 squared plus, this is going to be b times 1 times 2, right? Plugging 1 in for x, remember? And then plus 9 times 1, right? Because I'm plugging, again, plugging 1 in for x. What happens on the right-hand side of this equation? Well, you get 5 times 1 squared, so that's 5 plus 20 plus 6. So let's see what all this simplifies to. This is 6 times 4, which is 24, plus, what is that, 3b, right? Nope, not 3b, 2b, right? So plus 2b, b times 1 times 2 is 2b, correct? And then plus 9 is equal to 5 plus 20 plus 6 is 31. So it looks like 2b is equal to 31 minus 24 minus 9. So 2b is equal to, what is that, minus 2, right? Okay, 31 minus 24, 7 minus 9 is minus 2, or b is equal to -1. Oh, finally, just enough paper there, right? Okay, so there is my value for b. So you see how we found the value for b. Since we knew a and c, right, what they were, we just plugged those into our original equation. Yeah, the value for a and then the value for c. And then we used just any number that we wanted for x. We substituted that also. So I tried x to be 1, right? Okay, and I think I then solved there for, I'm hoping, solved for b correctly. B is equal to -1. Okay, so ooh, that was a pretty good algebra and arithmetic workout there, right? But we're only halfway through the calculus part of the problem, right? So I know a is equal to 6. So I have 6 over x plus b is equal to -1. So I have -1 over x plus 1. And then c was equal to 9, right? So I have 9 over x plus 1 squared, right? Now now I've got my integrand broken into 3 fractions. Now I'm going to break it up into 3 integrals, and I'm also going to factor these numerators out also at the same time. So I have 6 times the antiderivative of 1 over x, that's this fraction, minus antiderivative of 1 over x plus 1, and then finally plus 9 times the antiderivative of 1 over x plus 1 squared. And although I exchange now, right, one integral, now I have 3 integrals to do, so that seems like I've made the problem harder. Actually, I've made the problem easier because these 3 integrals are easy to compute. What is the antiderivative of 1 over x? Right, I believe that is natural log of x. So I have 6 times the natural log of x, right, minus, what's the antiderivative of 1 over x plus 1? Oh, I think that's the natural log of x plus 1. Now, for this last antiderivative, I can't use natural log, but because this is 1 over x plus 1 squared. But I can rewrite 1 over x plus 1 squared as x plus 1 to the minus 2 power. And now I can use the anti-power rule. So I have 6 times the natural log of x minus the natural log of x plus 1. And then plus, let's see, this is going to be 9 times. I think this would be x plus 1 to the minus 1 power. I add 1 to the exponent, right, and then divide by the new exponent of minus 1. Don't forget to add your arbitrary constant here. So the integration is all finished now. I have my antiderivative now, and we're going to simplify it a little bit. This would be minus 9 times 1 over x plus 1, right? Minus 1 goes into 9, minus 9 times, right? But then the x plus 1 to the minus 1 power, you can write that as the reciprocal. So that would be 1 over x plus 1. So altogether here, finally, we write this in the cleanest possible form. We would get 6 times the natural log of x, right? Minus the natural log of x plus 1 minus 9 over x plus 1. And then plus our constant. There it is. So there's our antiderivative. See, we were able to find it. That's a pretty complicated problem. That one is not easy, okay? That's a big rational expression. So finding its antiderivative, that's quite an achievement. And we were able to do that there, right? Okay, we come out with a pretty elaborate antiderivative, right? A pretty exotic antiderivative, but that was a pretty elaborate integrand that we were trying to integrate. So I guess it's no surprise that we got an elaborate antiderivative for that. Okay, I think that's pretty cool. If you can do that integration problem, then you are really pretty good at integration. All right, let's try another one here. All right, and so you can already see this one looks pretty complex, right? So so there is going to be a little bit of work involved here, and but notice that this denominator is already factored, right? As factored as we can make it, because we already have x squared plus 2 squared, right? So we've already got this denominator in factored form, but we cannot factor x squared plus 2. All right, so we cannot factor x squared plus 2. So this denominator is factored. It's completely factored. We're not going to be able to factor any further the x squared plus 2. But this is factored enough so that we'll be able to use partial fractions in order to integrate this. Okay. All right, I'm going to pause for a moment, and then we'll come back and we will look at how to integrate that with partial fractions. Okay, so let's try another example here of integration with partial fractions. So again, since the denominator here is already factored, then we can just sort of launch right in, right, to this this partial fraction process, right? I want to try to break this big rational expression, right, into smaller fractions, right, that maybe are easier to integrate than this original big monster here that we have in the integrand. So so our factors here of our denominator, right, since we have the x squared plus 2 squared, recall from the previous example, then you're going to have to write that as x squared plus 2 to the first power, right, in one denominator, and then x squared plus 2 to the second power, right, in a second denominator. So you're going to break this this big fraction into these two partial fractions, one of them with, again, x squared plus 2 to the first power. Since we have x squared plus 2 squared here, one of your fractions is going to be x squared plus, is going to have denominator x squared plus 2 to the first power, and then the second one will have x squared plus 2 to the second power. Okay. Now here's the second little catch that that you have to be careful of in this particular problem. All right, so in the previous examples, you would think, okay, I'm just going to have a numerator here. We'll just call it a, and then we'll have a numerator here, and we'll just call it b, right? Okay, but things are a little bit more complicated because this denominator is not it is a polynomial, right? Okay, x squared plus 2 is a polynomial, but it's not a first degree polynomial. This is a quadratic polynomial, and you cannot factor it into a first degree, into a product of first degree polynomials, okay? So this is degree 2, and because of that, that means that we want the numerator to not just be a constant a, but it can be actually a linear polynomial. It can have degree 1, okay? So it can have degree 1. It does not have to have degree 0. All right. Look, in the previous example, so you may be wondering, you know, what's the difference here, okay? In the previous example, look, for instance, at this first fraction in the partial fraction decomposition. So we knew the denominator here was going to be x. X is a first degree polynomial. So that means the numerator can be a 0 degree polynomial, but a 0 degree polynomial is a constant. So see, the a turned out to be just a constant. In this case, it turned out to be the constant 6, right? But the difference here is that this denominator in this partial fraction is degree 2. So we have to assume that the numerator might have degree 1, not degree 0 like a constant has, but it might have degree 1. And what do degree 1 polynomials look like? Well, those are linear polynomials, so they look like this. You have a, right, a constant times x plus another constant. So you have to write your possible numerator here not as just a, but as ax plus b, a first degree polynomial. And to do the same thing for the second fraction as well, okay? So we have to assume that it also might have first degree. So that means it's going to look like a constant times x plus another constant. But you can't write ax plus b again because we've already used ax plus b as the numerator for this first fraction, right? So you have to choose different constants here. Let's say cx plus d, okay? So here's the correct way of writing the partial fraction decomposition for this original fraction, okay? Again, started off the way you would use, the way we saw from previous examples, right? You would write ax squared plus 2 to the first power, and then ax squared plus 2 squared, right? Okay? But then it's the numerator that's going to be slightly different, because x squared plus 2 is a quadratic polynomial, a degree 2 polynomial. You have to assume that the numerator here can be a degree 1 polynomial, a linear polynomial, and linear polynomials look like something like this, right? A constant times x plus a second constant. So this numerator also has to look like a constant times x plus a second constant. All right, now we have to figure out, oh, now this has gotten a little more complicated, right? Because now we have to figure out what is a, b, and c, and d, right? Okay, so so it's really kind of messy now. All right, but we're going to go through very similar reasoning, right, to figure out what the a and the b and the c and the d are, okay? So recall now, right, when I add these two fractions together, right, ax plus b, right, over the x squared plus 2, and then plus the cx plus d, right, over the x squared plus 2, x squared plus 2 squared, right? When I add those things together, I have to come up with 8x cubed plus 13x, right? Okay, so how do we add these two fractions together? Well, you have to have a common denominator here, right? The common denominator is going to be x squared plus 2 squared, okay? X squared plus 2 to the second power. So this fraction already has the correct denominator. That's nice. So I don't have to mess with that second fraction at all. It's already got the correct common denominator for adding these two fractions together. But the first fraction now, I'm going to have to change that a little bit, right? Because I've got to multiply top and bottom by another factor of x squared plus 2, so that I will get in the denominator of the first fraction x squared plus 2 squared. So multiply top and bottom by x squared plus 2. So that's going to give you a little bit of algebra there, right? I have to multiply top and bottom by x squared plus 2. So in the top I'll get, I don't know why I wrote the, why did I put that there? Okay, so in the top there I'm going to get ax plus b times x squared plus 2 over x squared plus 2 squared, and then again this second fraction stays the same, right, because it's already got the correct denominator. So let's see, when I add these two fractions together, I get x squared plus 2 squared, right, and then divided into ax plus b times x squared plus 2 plus cx plus d. Okay. Now, again, right, that fraction, right, this fraction must be the same, right, as this fraction, right? So the ax plus b times x squared plus 2 plus cx plus d has to be 8x cubed plus 13x. So let's write down that equation that must be true, right? ax plus b times x squared plus 2 plus cx plus d has to come out to be equal to, what did I say there? 8x cubed plus 13. Okay, now let's, now what I'm going to do to figure out the A, B, and the C and the D, now I'm going to have to use a reasoning that's a little bit different than in my prior examples. Remember, in the prior examples, I would choose a strategic value for x and substitute, right? Hoping that if I chose the x carefully, strategically, right, some terms would drop out and I would be able to, deduce what some of these values A, B, C, and D are. Okay, that strategy is not, I don't think, is not as useful in this example. But so we're going to try something different here. So let me show you what I'm going to do. Let's go ahead and take the ax plus b and multiply it times the x squared plus 2. So let's see, what will that give me? Ax times x squared, that's ax cubed, right? And then ax times 2, that looks like 2ax, right? And then b times x squared is bx squared, right? And then b times 2 is 2b. Correct, right? B times 2 is 2b. And then plus cx plus d, and that's still equal to 8x cubed plus 13. Now, let's add terms together here, add like terms together on the left-hand side here. Notice you only have one x cubed term, so not going to be able to combine anything with that. But we do have, and then we only have also one x squared term, right? So not going to be able to do anything with that either, right? But I want you to notice that we have a couple of, we have here a couple of x terms. Let me erase something here because this looks funny. All right, that is cx plus d. Okay. All right. Now, so on the left-hand side now, notice we have this x term and also this x term. So I can add these x terms together by adding together their coefficients. So the number of x's you have here is 2a plus c. So I'm going to write 2a plus c times x, because that's how many x's there are on the left-hand side. And notice we also have here a constant, 2b plus d. These two terms don't have any x's in them, so I'm going to write them at the end here together, 2b plus d, right? Those two, these two terms are constants, so we can combine them also, equals 8x cubed plus 13. Now, you may be wondering why I was bothering to combine terms like this on the left-hand side. Well, here's why. The left-hand side equals the right-hand side, right? So notice that on the right-hand side you have 8 times x cubed, but on the left-hand side you only have one x cubed term, right? It's a times x cubed. So guess what that means? A has to be equal to 8. That's the only way the left-hand side and the right-hand side are going to come out equal to each other, right? So notice now you know that a is equal to 8. Hooray, okay? So there is one of my four constants that I'm looking for, right? I know that a is equal to 8, okay? Great, all right? So we're 1/4 of the way there. Now you see we can use that, right? Okay, because now here on the left-hand side, right? Okay, now I can fill in 8, right, for wherever I see the a, okay? Now, can I use that reasoning elsewhere? Ooh, I think so, right? Because look, on the left-hand side, on the right-hand side, you don't have any x squareds, right? You have 8x cubed and you have 13, but you don't have any x squares. But here you have b times x squared. So guess what that means? That means b has to be equal to 0, right? Because otherwise, you're going to end up with, you have to end up with an x squared here, right, on the right-hand side. So, ooh, there's my second. Ooh, that's a big thing to figure out there, that b is equal to 0. Oh, I like that, okay? So now we know that b is equal to 0. And now you can use that information, right, again, to help you with figuring out the other constants, right, the c and the d, correct? All right, now let's look at this third term. Here you have 2a plus c times x, right? But notice, again, on the right-hand side, there aren't any x's. So that 2a plus c, that has to be equal to 0, right? This coefficient must be 0, because otherwise you'll end up with x's here on the right-hand side. But there's not supposed to be any x's on the right-hand side. So you know that 2a plus c is equal to 0. But a is 8. So 2 times 8 plus c is equal to 0, right? Okay, so I think that tells me something about what c is. I think that means c is equal to minus 16, correct? Just solve this equation for c. 2 times a plus c is equal to 0 means c is equal to minus 16. Great. So there are, I'm just about done, right? I have I have 3 out of the 4 constants that I need. What about d now? Well, look, here you know that 2b plus d, that is a constant, right? Because it doesn't involve x. But so that's just a number. But on the right-hand side, what's the only number you have? You just have 13, right? So you know that 2b plus d has to be equal to 13. And that's really helpful because we already know that b is equal to 0, right? So we have 2 times 0 plus d is equal to 13. And there it is, right? Because, of course, 2 times 0 is 0. So there we know what d is, right? D is 13, okay? So, wow, there we have, right, our 4 constants in our partial fraction decomposition, okay? All right, so let's see if we can make use of that information. So let's see, what do we know there, right? We know that a is 8, right? So we have 8x over x squared plus 2, right? Okay. Plus c is minus 16. So I have minus 16 times x plus, what was d? 13, right? Yeah, plus 13. So plus 13, right? Over x squared plus 2, right, squared. There is my partial fraction. There now is my partial fraction decomposition. Okay, and now we're going to write these two. We're going to now write these two fractions, right, as simpler derivatives. Let me pull the, so I'm going to write the antiderivative of 8x over x squared plus 2, right? And then plus, and now the antiderivative of minus 16x, right, plus 13 over x squared plus 2 squared. Okay. So those now are the two antiderivatives now we have to compute, right, in order to finish this problem. So we now have two antiderivatives to calculate, right? But that's a little bit better than what we started with. Even though there are two antiderivatives now instead of just one antiderivative, these two antiderivatives now are much easier to deal with than that one big ugly antiderivative that we originally started with. And I think both of these now we have some idea of how we can treat them. Okay. All right. So let's take the first one, 8x over x squared plus 2. I think I would factor first out the 8, okay, from the numerator. So you would have x over x squared plus 2. And now I think this we can integrate by substitution, all right, because x is the derivative of, well, it's part of the derivative of x squared plus 2. Notice the derivative of x squared plus 2 is 2x, not just x. It's 2x, but that's close enough, right? Okay, so I think that's kind of a hint there that we can integrate this by substitution. This one I'm going to break up into, I think this I will break up into two antiderivatives, all right, in order to attack this one. Okay. All right, so let me pause here for a moment to catch our breaths here, right? Because that was already a lot of work to do the partial fraction decomposition, and then we're going to come back here now and finish off these two antiderivatives. Okay, it's a good thing I paused there because when I was paused, I noticed a mistake. This is why I need to have you guys in class with me, because you can help me find these mistakes when I make them. So let me fix this. This is a pretty easy mistake to fix. All right. I wrote something down wrong earlier. So when I was writing down this numerator is equal to the this numerator of my the sum of my partial fractions, right, is equal to 8x cubed plus 13, I inadvertently left off this x, right? The original numerator for the original integration problem was not 8x cubed plus 13, it was 8x cubed plus 13x, okay? So this all the way down here should have an x in it, right? And so that's going to change my constants somewhat. The a still comes out to be 8, and the b, by the same reasoning, will still come out to be 0, right? Ax cubed has to be 8x cubed, so that means a has to be 8, and b times x squared has to be 0 times x squared, because there is no x squared on the right-hand side, so I should have b equal 0, right? Okay, but the c and the d are going to now change slightly, because 2a plus c times x has to be the same as 13x. 13x, right? 2a plus c times x has to be the same as 13x. So that means that 2a plus c has to be 13, right? So you get, so now that you know a is 8, that means that 2 times 8 plus c has to be 13, which means that c is not minus 16. Actually, c is equal to minus 3, okay? So, so I got this slightly wrong value there for c, right? C is actually equal to minus 3. And then it's also going to change my value for d, right? Because notice that because this is 13x, and this is 8x cubed plus 13x, that means there's no constant on the right-hand side of this equation. There's no constant here. All these terms involve x. So that means that 2d plus c has to be 0, because there is no constant on the right-hand side of the equation. So I know that 2d plus c is 0, right? And of course b is 0, so 2 times 0 plus d is 0. That means that d is equal to 0, okay? So slightly different values now for these constants. So that changes here my my two partial fractions, right? This is going to be c is going to be minus 3. So I have minus 3 times x here, and then d is really 0. Okay, so there is no d term actually in this second fraction. And so now when I integrate, right, the two terms separately, I'm going to factor out the 8. So I have a times the integral of x over x squared plus 2, and then I'm also going to factor out this minus 3. So I have minus 3 times the integral of x over x squared plus 2 squared. And now I'm going to be able to integrate both of these by using substitution. Okay, so let's do that. So let's start with that first antiderivative. So I'm going to use substitution, and in the usual fashion, I'm going to let u be equal to the denominator here, which is, of course, x squared plus 2. So that means du dx is 2x, right? And now when we solve for dx, of course, we get that dx is equal to du divided by 2x. So this is what I will substitute for dx, right? So I have antiderivative of x over u, because u is going to be x squared plus 2, right? Okay, and then times dx here, but dx is du over 2x. Now, I'm actually going to make this exactly the same substitution in this second integral. I'm also going to let u be x squared plus 2. So I don't have to do a second substitution here. I'm going to do don't have to choose a separate quantity to let be u, right? In substituting in this second integral, I can still let u be x squared plus 2, and then dx is still du over 2x. So this would be minus 3, and then antiderivative of x over, but now notice it's u squared, right? Because this is x squared plus 2 squared, and then again dx is du over 2x. Here I can factor out the one. This is 1/2, so I can factor that out with the 8. So I get 1/2 times 8, right, times the integral of the x's divide out. So I just get integral of 1 over u du. And for the second antiderivative, I can also factor out the 1/2, so I get minus 1/2 times 3, antiderivative of the x's divide out, so I get 1 over u squared du. Okay? Well, of course, 1/2 times 8 is 4, right? So we have 4. 1 over u du that we want to integrate, minus, here I have 1/2 times 3, so that's minus 3/2. And this 1 over u squared, I'm going to write that as u to the minus 2 power, because I'm going to integrate that using the anti-power rule, correct? All right, so how does 1 over u integrate? You know this very well. That's the natural log of the absolute value of u, right? And how does u to the minus 2 power integrate? Well, that's just the anti-power rule. So we get u to the minus 1 over minus 1, right? Add 1 to the exponent and divide by the new exponent. And don't forget our constant here, but we're almost done. So we have 4 natural log of the absolute value of u, right? And then let's see, you're dividing by minus 1, so that's going to end up being plus 3/2, right? And then u to the minus 1 is 1 over u, correct? And now, finally, let's undo the substitution, but u is x squared plus 2, so we get 4 times the natural log of x squared plus 2, plus, it looks like 3 over 2 times x squared plus 2, right? U is x squared plus 2, and then plus our constant. At last, okay? There is our, there it is. There's our antiderivative. So a nice big antiderivative, right, for that original integrand. Wow, okay? So there's a very complex integration by parts problem. That's a very complex integration problem. That's about as challenging as the integration will get, I think, this semester, because you had to do partial fractions here, right? And this wasn't a simple partial fraction to determine. And then even after we had broken our integrand up into partial fractions, right, we had to use integration by substitution, and that involved, right, using natural log to integrate, and also the anti-power rule, right, to integrate as well. So we really exploited a lot of things that we've learned in the course, right, in that problem. Okay, now there's a video example for this one, I think, that's in your partial fraction homework, but I just want to start this problem for you, just to remind you that you don't always have to rely on these advanced techniques, right, to do your integration. Be watching for the simplest technique possible, right, in order to carry out your integration. So when you see this one, you might immediately think, oh, I'm going to use partial fractions to integrate this. But look, notice that if you look at this denominator, what is its derivative? Its derivative is, well, the derivative of x cubed is 3x squared, and the derivative of 3x is 3. So that means that the derivative of your denominator is already in your numerator, and when you have that situation, that means you're probably going to be able to integrate by substitution, right? So my suggestion here is to let u be x cubed plus 3x minus 4, right? And then notice du dx will be the numerator here. It will be 3x squared plus 3. And then, of course, that means that dx is going to be du over 3x squared plus 3. So when you substitute u for the x cubed plus 3x minus 4, and then you substitute this fraction for dx, right, notice what happens. You get this integrand, and that simplifies, right, very nicely, because these two things will divide out, right? And so you end up with the antiderivative of du over u, and you know how to integrate that, right? That you can integrate easily using natural log, and then you just undo your substitution. So you don't have to use anything fancy here to integrate, even though this is a complicated integrand, right? It's a complicated rational expression. It really is not difficult to integrate, right? Just with straightforward substitution. So now that we've learned, these more sophisticated integration techniques, don't lose sight of just plain old integration by substitution, okay? Sometimes that's enough, right, to allow you to do an integral. Okay, let's see how much time we've used there. All right, so we're a little bit over an hour, so that's probably enough to keep you busy. And our next topic, as I mentioned, will be a more advanced, our final advanced integration method, and that's called trig substitution. Okay, so that's a type of substitution, but it involves, as you can tell, trigonometric functions. So we're going to take that up in next Monday's lecture. So that will be the Monday, April 6th, I guess, if I'm counting right. Okay. All right. So I will see you then on Monday, April 6th, right? So be working on your homeworks, right? The homeworks that are posted, right? Because remember, the test is going to cover through integration by partial fractions, right? Okay, our test number 2. All right, so see you guys later. Keep safe, right? Stay indoors as much as you can, right? Don't touch anything. Wash your hands. All of this advice that we're getting, right, for preventing, getting sick, right? So take heed of that advice. All right, see you later.